Hi, my name is David Ju Young Kim, and today I will be presenting my research on full 2-pi tunable phase modulation using avoided crossing of resonances, which was published in Nature Communications 2022. The objective of this paper is as follows. Imagine a metasurface. If light impinges on it, and it's a reflective metasurface, then light will be reflected off. What we want is to have a dynamic control over the spatial phase distribution of the reflected waves. I'll elaborate using an example of a beam steering metasurface. Let's say the left meta-atom reflects light with an arbitrary phase. If the central meta-atom reflects light with a phase difference of pi/2 from that of the left meta-atom, and the right meta-atom imparts a reflected phase that has an additional pi/2 phase difference from the central one, and we could do this by electrostatically gating each meta-atom. So for example, 3 volts, 7 volts, and 11 volts. By linking the points on the waves that have the same phase, aka the wavefront, we can see that the light is reflected at an angle. We want to be able to dynamically change the phase with a full 2-pi phase range, and we don't want to have a non-uniform distribution of the amplitudes of these waves. Why do we need this functionality? Well, there's various applications for such a piece of technology, including on-chip reconfigurable lenses, LiDAR, information optics, and active holography, to name just a few. The physical mechanism of how this works is based on optical resonances. If light is shone on a meta-atom, then charges such as electrons oscillate back and forth with the electromagnetic field. The oscillating charges then emit their own radiation, but as you well know from the dynamics of a spring oscillator system, there is a phase lag depending on the resonance frequency of the system and the driving frequency. This phase lag is what we're going to be actively tuning by changing the resonance frequency on demand with respect to the driving frequency, which is fixed. By electrostatically gating meta-atoms and applying different voltages, we can effectively input or take out charges that oscillate with light, which changes both the effective K and the effective M that goes into the resonance frequency equation. You can see that the phase lag changes depending on the frequency ratio of the driving frequency and the resonance frequency. Notice also that the geometry of the meta-atoms are important, as they can affect the resonance frequency as well. To achieve our goal, we had two major problems to tackle. The first one was the issue of phase amplitude correlation. This stems from the fact that the scattered light is emitted by resonances, which has the biggest amplitude at the resonance frequency. Our solution to the correlated phase/amplitude was to overcouple the resonance to the incident light. What I mean by overcoupling is, when light impinges on the meta-atom, there is a portion of light that reflects without interacting with the oscillating charges. This is depicted by the yellow arrow. The coupled portion of light is the light emitted by the oscillating charges, and this is depicted with a green shaky arrow. Overcoupling means to have nearly all the light that is reflected back to be in the form of the emitted light from the charges, which is the green arrow, and not in the form of the yellow arrow, which is the light that didn't interact with the oscillating charges. By overcoupling, the reflection amplitude approaches unity throughout the frequency range in the vicinity of the resonance frequency. This is nicely depicted by the large circle shown in the picture. The alpha corresponds to the tuning parameter, aka the applied voltage. We also show the undercoupled case for contrast, as undercoupled resonances only draw small amplitude circles on the complex reflection amplitude space. This means that as the phase changes, the amplitude constantly changes as well, preventing phase-only modulation. The second major problem we had to address was the trade-off issue between the resonance shift and the line width. Because the idea of dynamic phase modulation using solid-state methods such as electrogating is to impart more or less charges into the resonance itself, if we want a larger resonance frequency tuning, we need to cram in to the system more charges. A problem with this is that the more charges you put in, the more losses you have, and this results in a broader resonance curve. This is depicted by the FWHM which stands for full width half maximum. The lateral shift of these curves, denoted by delta omega, needs to be bigger to attain the full 2 pi phase range, but in the process of trying to maximize the delta omega by cramming more charges in and out of the system, you inevitably get larger full width half maximum due to more losses from the extra charges, which then in turn requires you to have an even bigger delta omega. This is a trade-off relationship, so people had to settle for a sub 2 pi dynamic phase range. Our solution to the trade-off issue was to use an avoided crossing between two resonances, one being an overcoupled spectrally narrow resonance, and the second resonance being a resonance with a high resonance tunability. A spectrally narrow resonance means that it has a narrow full width half maximum, and a high resonance tunability means that the resonance frequency changes greatly even with a small change in the tuning parameter alpha. A spectrally narrow resonance, due to the trade-off issue discussed in the previous slide, will not have a high resonance tunability, and so using an overcoupled spectrally narrow resonance would have granted you uniform amplitude, but not a full 2 pi phase modulation range. This is where the phenomenon of avoided crossing plays an important role. Look at the picture on the right. The first overcoupled resonance, which inevitably has a small resonance frequency change due to the trade-off issue, is depicted by the red line that is more horizontal than vertical. The secondary resonance with a high resonance tunability is depicted by the red line that is more vertical. The more vertical nature expresses the high resonance tunability, as it means even a small change in the control parameter alpha leads to a big resonance frequency change, leading to a large gradient. An avoided crossing between these two resonances then allows for the secondary resonance to push the first resonance over the operating frequency, which is denoted by omega 0. This grants the first overcoupled resonance the tuning speed of the secondary resonance, while keeping the overcoupled nature due to the hybridization of the two resonances. This allows the system to acquire the best of both worlds and have more than 2 pi dynamic phase range while keeping uniform amplitude, which is shown in the picture on the left. I'll briefly explain what an avoided crossing is. If you have two resonances, denoted 1 and 2, they naturally have different charge oscillation patterns, as you can see on the top of the slide. As the two resonance frequencies approach one another, the charge oscillation pattern for one resonance gets affected by the other charge oscillation pattern, and vice versa. This leads to a hybridization of the two resonances, and each resonance acquires characteristics of the other. This affects their resonance frequencies, and naturally, the resonance frequency does not draw a straight line as it would have had there not been the presence of the other resonance. If the interaction between the two resonances are zero, then the two resonances cross one another in the frequency space as if nothing happened. This is nicely shown by the GIF file that tunes the interaction strength W. As the interaction strength approaches zero, the two resonances cross one another in straight lines, whereas for finite interaction strengths, the resonance frequencies avoid one another, hence the term avoided crossing. So to summarize, an avoided crossing between an overcoupled spectrally narrow resonance and a resonance with a high resonance tunability grants you hybridized resonances that have the best of both worlds. To realize this idea, we came up with a proof of concept metasurface example that utilizes a QBIC and graphene plasmons. The QBIC is the overcoupled spectrally narrow resonance, and the graphene plasmons correspond to the resonance with a high resonance tunability. The very nature of the QBIC, which allows for the tuning of the radiative coupling of the resonance through geometric parameters such as the inner shift of the two pillars, denoted by delta in the picture, can lead to an overcoupled and spectrally narrow resonance. The graphene plasmons, on the other hand, possess highly confined electric field profiles constrained to the graphene layer, and by gating the graphene layer, the resonance frequency of the graphene plasmons can be greatly tuned. The picture on the right shows the zone folding effect due to the doubling of the periodicity from the inner shift of the two pillars. Had there been a zero shift, there would not be a resonance at kx equals 0 between 0.25 and 0.5 normalized frequency, but with the inner shift, the zone folding results in a resonance in between 0.25 and 0.5 at kx equals 0. This is our QBIC. As you can see in this slide, the electric field profiles of the QBIC and the graphene plasmons are quite similar, and this leads to a significant overlap integral between the two modes. This equates to having a large interaction strength between the two resonances, which ensures significant avoided crossing. Our metasurface performance is shown as follows. Our avoided crossing metasurface is shown below, whereas the top metasurface is designed in a way that it doesn't host graphene plasmons, and therefore no avoided crossing. This is quite simply done by using an unpatterned graphene layer beneath the pillars, as the graphene plasmons that are excited won't be resonant from the reflection from the graphene edges, as it would be in the bottom metasurface with graphene ribbons. The top metasurface only hosts the QBIC, and due to the trade-off issue discussed earlier, the resonance only draws a sub-2 pi phase modulation range despite having uniform amplitude from its overcoupled nature. In contrast, by utilizing an avoided crossing with graphene plasmons, the bottom metasurface shows 3 pi phase modulation range, the extra pi phase change having come from the graphene plasmon itself. So in a sense, an avoided crossing between two resonances grant an upper limit of 4 pi for the dynamic phase modulation range. The control parameter is the graphene Fermi level, which was changed from 0 eV to 1 eV. This is a comparison chart of our metasurface compared to other active phase modulation devices. As you can see, our device is superior in the phase modulation range and also the best in reflection intensity among charge carrier tuning devices. The thermal opticase shown below does grant higher intensities, but due to its tuning nature, it's quite slow and difficult for spatial control, as it is hard to impart different temperatures to different meta-atoms. This concludes my presentation, and for further inquiries, please contact either the corresponding author, Professor Min Seok Jang, or me through the emails. Thank you.